organizing program, and thank you for inviting me. So I would try to do justice to this topic, which says geospatial inputs for hydrological modeling. So we'll mainly focus on few of the hydrological models that are generally being used, and while discussing them, we will also discuss how we can generate their inputs using geospatial technology. So I think all of you are aware of with this term geospatial technology, because I think this is the third day of training. So faculty before me must have discussed this. So will it be fine if I switch off the camera and I'll keep on talking? Then in the Q&A we can I'll use the camera.
Sir,
okay.
Sir, actually we
yes.
want your video because it will go to the YouTube channel.
Okay, but the problem is when I keep this camera on, my video is also coming on my. So how to hide it?
No, just click your PPT.
Okay, fine. Thank you. Okay, fine. So let me start. So the topic today is geospatial inputs for hydrological modeling. Now, first of all, we have to understand when we talk about hydrological modeling, the primary input for all the hydrological process on land is precipitation. And the problem with countries like India is, one, the annual precipitation that we receive is not evenly distributed over the space, over the time. As you can see here, out of total annual precipitation, 70 to 90% occurs in the span of 3 to 4 months, which is the monsoon season. The special variation of precipitation is of the order, somewhere we receive somewhere around 120 mm rainfall annually, and in other places, specifically in northeastern region, we receive more than 12,000 mm rainfall in a year. So there is a disparity of distribution of rainfall. So each land parcel, when I'm saying land parcel, we are talking about watershed. So each watershed will have its own behavior towards this input. A watershed that receives less rainfall may generate less runoff. The watershed that receives higher rainfall may generate higher runoff. But this is only a qualitative judgment. When it comes to water, you need a quantitative assessment, and the hydrological modeling helps us there. So before we venture in the domain of hydrological modeling, let us understand the hydrological cycle, which I hope all of you are aware of, because the water moves in a cyclical fashion, so we call it a hydrological cycle. So starting from precipitation, it will come down in terms of either rainfall or snowfall. Then if it is snowfall, snow will get accumulated. If temperature rises, it will melt. If you are receiving rainfall, there will be interception by the vegetation or the top cover that we have. Then the remaining water will come down as a direct throughfall. Some of that will come as a direct rainfall, and there will be leaf drainage. Now whatever water coming towards soil will absorb it and will infiltrate that water. Extra water infiltrated will percolate down and will join groundwater. Now the excess surface water will start flowing on the surface due to the let's say terrain properties, the slope and total head of water. So it will first fill the surface depressions, which we call ponds and reservoirs. Now the excess water will again flow into streams. It will join bigger reservoirs, ponds, or even oceans. And from all these surfaces, from snow to leaf surface to wet soil to water bodies, the evaporation plus transpiration will continuously happen. So again, water will go into atmosphere. It will find a nuclei. It will form a cloud will precipitate, so the cycle will complete. Now, if you want to truly quantify the hydrological elements, you need to quantify each and every one of them. The problem is hydrological models that we generally use, they mainly focus on one or two of them. So you may have a good hydrological model which works fine for estimation of surface water runoff, maybe a little bit okay for base flow, but it might not work well for estimation of groundwater recharge, or it might consider a lumped approach for estimation of interception, or let's say infiltration, or soil moisture, or maybe snow melt. So if you want to solve this problem of water resource assessment, you need a model which gives similar emphasis to each one of these components. And in the latter part of this presentation, we will see one or two of these kinds of models. Now we have to understand what is a hydrological model and how complex is it to model the hydrological process. So in simple terms, the river basin is very complex and the river basin is very complex and mainly depends on basin characteristics and characteristics of the climate. So this diagram here tries to, let's say, show you how complex or what parameters, what interrelation exists between parameters and what parameters govern the stream flow. I am only talking about stream flow here. As I told you in a previous slide, there are various hydrological components. Evapotranspiration is one of such component, infiltration is one of such component, soil moisture is one of such component, percolation and deep percolation is one of such component. So there are various components, but if we were to plot the relation between, just a minute. Yeah, sorry. So if we were to develop a box plot of or a flow chart of what components and how they affect each other in terms of surface runoff, so you can see dominantly the surface runoff is governed by surface cover properties, like what kind of vegetation is there, what kind of land surface is there, are there water bodies, what kind of soil we have, what kind of aquifer we have, and then each one of these components will, like vegetation will interact with the land surface characteristics, soil will interact with the vegetation, vegetation will interact with the soil. Somewhere you have a deep clay soil but you don't have vegetation, so there will be less transpiration. Somewhere you have a very deep and clay soil and you have very healthy dense vegetation, so losses due to transpiration will be much higher. Now somewhere you have groundwater very near to surface, so it will also contribute into the stream flow. Somewhere you have a very deep groundwater, so most of the infiltrated water will join that groundwater as a percolation and base flow will be almost minimal. So all these components interact with each other, and it is simply impossible to keep track of all these interactions in a qualitative term. So we have to venture into a quantitative domain. So we use hydrological model. In very simple terms, hydrological modeling involves the application of mathematical expressions that define the quantitative relation between the inputs and the outputs. Input means the characteristics that govern the hydrological parameter, in this case runoff, and the hydrological parameter itself, which is a runoff. So mathematical relation between the characteristics that govern generation of runoff and the value of runoff. So that mathematical relation is called hydrological modeling. Now, why do we use hydrological model? Why we go for hydrological modeling? To understand those processes and to also understand that if a particular characteristic changes, what impact it will have on the outcome. Because this, if this happens, what will happen? Answering this is a very critical part of resource management. Many times we require hydrological modeling for, let's say, dealing with the extreme events like flood and drought also. Now we'll briefly see types of hydrological models. So we generally discuss about lump model, distributed model, conceptual model, then physically based model. So you have to understand what these models, what these terminologies are. So lump model, basically you can say this as this is a black box model, where it do takes into account what is happening, but it doesn't takes into account where it is happening. So in a watershed, if you have 2-3 different types of soil, 2-3 different types of vegetations, their response towards runoff generation will be different. Whereas lump models will assume that entire watershed as one entity and will model the runoff using that assumption of one entity. On the contrary, distributed models don't assume those things. They either divide that area into square or regular shaped pixels, cells or in a homogeneous areas, and then they try to solve the hydrological processes on those pixels or grids or those homogeneous areas. Classic examples are the SWOT model, soil water balance. So SWOT model, HEC HMS model, they distribute your area into homogeneous areas, which we generally call as HRU or sub watersheds or micro watersheds, and variable infiltration capacity model, which we'll see in coming slides. It discretizes the watershed into small square pixels or square grids, and then try to solve the hydrological process for each of those grids. So this is a distributed model. Now there is one more classification of model: empirical, physical base, and conceptual model. Empirical is if you establish simple linear or any kind of regression relation between the observed inputs and observed outputs, and you extrapolate that relation to unknown area, that will be called as an empirical model. Now, a physically based model will try to convert the actual physical process in terms of mathematical, let's say, formulas. Those are called physical based model. And as you can understand, physically based models are very complex. They require huge number of input parameters. So generally in practical hydrology, empirical or semi-empirical based models are the most famous ones. Now there are one more criteria also. There is criteria that is called event based or continuous model. Like you have event based model which will calculate the hydrological behavior for individual event, or you have continuous models which will keep on calculating those for every day. So there are different types of or different categories of the hydrological model. Now comes the question, if there are, you have various categories of models, you have various models also. There are n number of models available in literature for solving the hydrological modeling problem. Now, how should I select a best model for my study area or for my objective? The criteria could be based on space discretization, how the hydrological processes are represented, how the vegetative layer on the surface is represented by the model, how the soil layer is represented by the model, and then we will rank them. For example, in terms of space discretization, if the model assumes your entire area as a one entity, so it's a lump model, I will give it a low ranking, or you should give it a low ranking. If it's a semi-distributed model like HRU, elevation bands and hill slopes or sub-basins, I'll give that model as a medium ranking. And if it is a truly distributed model, I will give that model highest ranking. Now in case of hydrological processes, if it replicates process using an empirical approach, we should give it a low ranking. If it employs a conceptual approach, now see, in conceptual approach, you have conceptually solved the process, but you might not have converted all the steps in a mathematical formula. Somewhere you will use empirical approach, somewhere you will use physical approach, somewhere you will use assumptions, and then solve the entire process. So this is called a conceptual approach. So if it's a conceptual model, we can give it a medium ranking. If it is a physically based model, highest ranking. Now, if a model presents vegetation as a single layer, lowest ranking. If it is present as a two layer, medium ranking. If it represents vegetation also within an area, if it gives option to give only one vegetation type, lowest ranking. If it gives you two vegetative types, medium ranking. And if it allows you to define that vegetative layer into different multiple layers, highest ranking. Similarly, soil, more the discretization in terms of soil, higher should be the ranking. But one thing we should keep into account, that a simple model structure does not reflect a complexity of, here I'm writing rainfall runoff, but hydrological response. And a complex model structure is not always supported by available data. So a balance between complexity of model and available information is crucial for successful model identification. So this line says everything. Not all the times the simple model will represent the process correctly. On the other hand, not all the time the complex model, you are at a position to solve that model because of limitation of data. So what you need to have a trade-off between, okay, what data I have. So with this data, which is the best suitable model that I can go for. And that's how you should choose a model, because this is a case specific or person specific choice. A model that is best suitable for you, for your area, might not be best suitable for somebody else's area, because that somebody may have more number of data or less number of data, or the objective of your study and somebody else's study might be different. So you can select the models based on their properties. You can select out of Heck HMS, you can select from SWOT, Mike-Shi or WIC. So there are various models. I have listed here the properties based on what are their advantages, what are their disadvantages, what it calculates, how it calculates, whether it goes for empirical or physical based approach, and then what outputs it gives. So if you have this kind of comparative table, as well as if objectives of your study are clear, you can choose a hydrological model. Now comes the core part of our today's discussion. We know what hydrological models are, but the point is what inputs I can get from geospatial technology to implement those hydrological models in a better, smarter, more accurate ways. So in terms of hydrological modeling, what geospatial technology offers us is, first of all, every hydrological model requires information about terrain, topography, and geospatial technology, remote sensing, provides us very highly accurate digital elevation models. You can even go for digital terrain model, or you can go for digital surface model. Nowadays, SRTM, Aster, Carto DEM, GTOPO, there are many Merit DEM is available, many DEMs starting from 1 kilometer by 1 kilometer resolution to somewhere around 1 meter by 1 meter resolution DEMs are available. Now, please understand 1 meter by 1 meter resolution DEM, anything below 30 meter by 30 meter falls under the category of commercial DEM, so that you might have to procure. However, anything coarser than 30 meter and 30 meter, it's available free of cost on various websites. Now, from those DEMs, we can derive surface topographical parameters like drainage, aspect, flow direction. We can, using that, you can generate drainage network, you can delineate watershed boundaries, you can derive morphological characteristics of a watershed, which are very essential for both understanding the behavior of watershed as well as quantifying the behavior of, when I'm saying behavior, I'm talking about hydrological behavior of watershed. Other set of inputs that geospatial technology offers us is the meteorological inputs like rainfall. We can always go for ground observed rainfall, but there are many areas, even in India also, where we don't have observatories, rainfall observatories we don't have. So in those areas, satellite-based rainfall retrieved using TRMM, GPM, then CPC data, INSAT-derived data, all these data sets can be used. Maybe they are coarser resolution, but it is always better to have some data than having no data at all. We can use temperature data. The satellite derived temperature data may not be that useful for hydrological modeling aspect, because that temperature is a columnar, it's a temperature profile, but we are mainly interested in temperature near Earth's surface, which satellites don't give that much of accuracy. However, you can use reanalysis data generated using GCMs and RCMs, where satellite data goes as a assimilation product. So that can be used. Radiation data, which we can derive using remote sensing, which we can use observed data, or we can use a reanalysis data. Then other meteorological parameters can also be used for hydrological modeling. Now, land surface parameters like land use, land cover, soil moisture, land surface temperature, albedo, evapotranspiration, snow cover, snow water equivalent, change in snow water equivalent, all these parameters can very well be derived using remote sensing inputs, and these are very essential parameters in hydrological modeling. In coming slides, when we discuss hydrological models, you will get to know where the remote sensing or geospatial technology is helping us in generating inputs or using to validate the output. Now, as you know, runoff from a watershed depends on rainfall characteristics, catchment characteristic, and climatic factors. And the interrelation between all these characteristics is very extreme. So it's very complex. So we have to go for a mathematical approach. So hydrological model is a mathematical expression between inputs and outputs, as we already have seen. So we will see some classic hydrological models published by researchers for estimation of surface runoff. So there is one called Benny's percentage model, where Sir Alexander Benny used the observed data of a small catchment near Nagpur to estimate the relation between cumulative rainfall and cumulative runoff. And what he found that the cumulative rainfall and cumulative runoff have similar curves. So he has then used this, he has exploited this, that we can derive this relation in terms of percentage, that how much percentage of cumulative precipitation or rainfall will get converted into cumulative runoff. And this study he has done in 1869 to 1872. So this is way before the independence. And then he has extrapolated this model towards many watersheds in Madhya Pradesh and Vidarbha region of Maharashtra. Then there is a Barlow's table which tries to correlate runoff with the precipitation, and this kind of table he has published that for different catchments. So class A catchments are the flat catchments cultivated and a specific kind of soil, then maybe an average catchment, a hilly catchment, very hilly catchment. Then he has done this analysis for various seasons also. So maybe season 1 is a light rain, no heavy downpour. So maybe he's talking about winter rainfall. Then season 2 is a average or varying rainfall, but no continuous downpour. So maybe he's talking about summer season. Season 3 is a continuous downpour. So he's talking about a monsoon season. So for these 5 types of catchments, these 3 types of seasons, he has calculated the runoff coefficient. So if you know in which catchment you are, what kind of season you are in, you can pick this runoff coefficient, multiply this with the observed precipitation data, and you can calculate the runoff. Okay. Then you must have studied these 2 formulas, English and D'Souza's formula, Khosla's formula. All of these were empirical in nature because these people have used the observed data of input parameters and output parameters, which is basically runoff, and they try to generate a relationship between the rainfall, dominantly rainfall. Some of them try to generate relationship between rainfall, soil type, and season with the runoff. Now, recently, one method has gained more popularity over all other methods, which is the soil conservation service curve number method. It is also known as hydrological soil cover complex number method, or curve number method, or NRCS method, like natural resource, because this soil conservation service of USDA was renamed as natural resource conservation service. So instead of calling it as a SCSCM, now we call it as a NRCSCM. This is a basic formulation of a curve number method. I believe many of you must have studied this or must have gone through this. So basically what we try to say here is that runoff is a function of curve number, and curve number is a function of soil type, land use, vegetative cover, antecedent moisture condition in your area. So how it goes? If you know the curve number, which is a function of soil type, land use, vegetative cover, soil, land, vegetative cover, and antecedent moisture condition, you can calculate the maximum. See, S is a potential maximum retention. This is the maximum water that can be retained by the area. Now, once you have that, you can calculate relation between discharge, runoff, and precipitation using this formula, which says precipitation minus initial abstraction. This IA is the initial abstraction. So precipitation minus initial abstraction, square of this quantity, divided by precipitation plus 0.8 of potential maximum retention. So this ratio will give you Q. Now mathematically you can understand. Mathematically, if curve number is 1, curve number is 100, what will happen then? This S will become 0. If S is 0, So this will become 0, this will become 0. So the mathematical equation will be Q is equal to P square by P. So effectively P square divided by P will be P. So basically the entire runoff will be converted into entire rainfall will be converted into runoff if curve number is 100. On the other extreme side, if curve number is 0, then this S will become infinite. So this P minus 0.2 of infinite and this Q plus 0.8 of infinite. So you cannot solve it. So basically Q will be 0. Q will become 0 because you are not able to solve this. So what it means that the curve number 0 means no runoff, curve number 100 means 100% runoff. So this is a relation between curve number and runoff. But you have to understand curve number is a function of soil, vegetation, antecedent moisture condition, and recently we have made it a function of terrain properties also. So let us see how this can be solved and where remote sensing or geospatial technology can help us. Now to solve this, when we talk about soil, we are interested in infiltration rate or infiltration capacity of the soil. So what USDA has done, USDA has classified soil into 4 categories, category A, B, C, D, where category A represents low runoff potential soil, means it is a soil with high infiltration rate, and category D represents highest runoff potential soil where you have very low infiltration rate. So a soil with highest runoff, highest infiltration rate will have low runoff rate. The soil with lowest infiltration rate will have high runoff rate. So the low infiltration rate soil will be put into D category and highest infiltration rate soil will be put in A category, and similarly A, B, C, D. So what we need to do with the soil data, you have to understand their infiltration properties and you have to categorize them into hydrological soil group, which is called ABCD in this case. Then how to select curve number? As I told you, curve number is a function of land use, land cover and soil type. So for all the soil types and for all the land use, land covers, there are nomograms available that if your land use, land cover is X and your soil type is B, so your curve number should be 98. But we already have discussed that curve number is also a function of antecedent moisture condition, which physically means how moist, what is the status of moisture in the soil. Because you all know 10 mm rainfall on a saturated soil will generate 9 mm of runoff, whereas 10 mm rainfall on a perfectly dry soil may not generate even a drop of runoff. So runoff generation is also governed by moisture content in the soil. So to continue our discussion, this table will help us in finding out the correct curve number as a function of land use and soil type. However, function of terrain and function of soil moisture. So to make curve number function of soil moisture, one more loop has been added in this SCS curve number method, which is a AMC class. So we will classify our area into 3 antecedent moisture condition classes: class 1, class 2, class 3. Basically, class 1 means we are talking about dry condition, class 3 means we are talking about wet condition, and class 2 we are talking about average condition. Now this dry, wet, average condition, these are qualitative measures. We need quantitative assessment. So how we do that? For doing that, we divide the entire time period into 2 seasons: dormant season and growing season. Basically, growing season is a monsoon season, dormant season is a non-monsoon season. So in a non-monsoon season, if your last 5 days rainfall is less than 12.7 mm, we will call that area to be in AMC condition 1. If last 5 days rainfall is between 12.7 to 27.9, we will call that area to be in class 2, average condition. If the last 5 days total rainfall is more than 27.9, we will call that area as a saturated area. Now these numerical definitions will change in terms of growing season. In growing season, if last 5 days rainfall is less than 35.6, AMC condition 1. If it is between 35.6 and 53.3, AMC condition 2, and greater than 53.3, AMC condition 3. So we will first take the soil map. We will convert that soil map into hydrological HSGs, hydrological soil groups. Then we will cross the soil map with the land use, and we will take help of these standard nomographs, what kind of land use, what kind of soil. So what should be the curve number at AMC condition 2. The table I'm showing you here gives me the value of curve number if my watershed or if my area is at AMC condition 2. So basically, if it's a dormant season, last 5 days rainfall is between 12.7 to 27.9, and if it's a growing season, last 5 days rainfall is between 35.6 to 53.3. So if this is true, my curve number which I have selected in my previous step is correct for me. But this may not remain true throughout my study time period. The last 5 days rainfall may become more than 27.9, or it may become more than 53.3. Then what I have to do, I have to correct my curve number for the antecedent moisture condition. So how we correct it? There are various formulas available, out of which we generally prefer this Chauvin's formula for converting curve number 2 to curve number 1, and I mean from curve number of AMC condition 2 to curve number of AMC condition 1, and Hawkins formula to convert curve number 2 to curve number 3. So now what you have done, using rain AMC data, soil data, land use data, you have derived curve number for each and every day. Then you can calculate the S, potential maximum retention, and you can calculate the Q. I also have said during introduction that curve number should also be a property, or should be function of terrain, which in traditional approach it is not. But in recent approach, people have used slope and corrected the curve number. So what the procedure goes like this: you first derive or decide the curve number 2, then you take help of slope map to rectify that curve number 2 as a slope adjusted curve number 2. Then you analyze the AMC conditions and convert the slope adjusted curve number 2 into curve number 3 or curve number 1, as the case may be. And once you have done that, so this is a flow chart. Once you have calculated this curve number 1, 2, and 3, put that in this equation of potential maximum retention. Once you have done this potential maximum retention estimation, then you calculate this runoff. So I will show you a very small case study wherein it will be clear to you how remote sensing or geospatial technology helps us in doing this. So this case study belongs to a Solani watershed, which is in the Ganga basin. The Solani river is a tributary, small tributary of Ganga river. It joins somewhere near Luxor. Confluence is near Luxor. So now what data we have used, or what data you may need? Of course, you require meteorological data. So in this case, we have used point observed rainfall data. If you don't have, you can use IMD gridded data, you can use TRMM data, CPC data, or GPM data. In last part of my discussion, I will show you different sources from where geospatial data can be obtained. Then we have used remote sensing image to convert that image into land use land cover map, because to generate curve number I require soil map and I require land use land cover map. So remote sensing has helped us in generating this land use land cover map. Other important inputs were DEM, SRTM DEM that I have used, which is also a remote sensing product, and soil information. Well, of course, the soil information, these soil maps were generated using field surveys by my colleagues at IIRS, but those maps were converted into a geospatial data using GIS software. So this also falls under geospatial inputs. So what was the first step? Using DEM and using the hydro processing, we have delineated the catchment. So this is how the DEM is processed. The fill sync is done, then flow direction is calculated, flow accumulation is calculated, the drainage network has been delineated by defining the stream generation threshold. Then after drainage network, we have converted into stream ordering. Once the streams were ordered, catchment, small sub basins or sub watersheds, micro watersheds or uh, sub catchments were delineated and they are represented here. After this TM processing, land use land cover was mapped. Now for mapping land use land cover, we have collected some ground observations to train the classification algorithm, and we have reserved some field observations to validate our land use land cover classification activity. Now you can see here forest covers around 30%, which is a hilly area of this watershed, and 50% of area is covered by agriculture, and remaining 20% is covered by water bodies, then settlements, barren lands, and other things. Now, soil map through extensive soil surveys in that area. Colleagues from IRS have generated this soil map, and they have generated that soil map in terms of geospatial data. Now see, during field work, this is how you can collect the ground samples or ground truths, and you can link them to the either raw data or classified data using GPS, observations of GPS. So this is a soil map, and this is the land use land cover map. This is a simple how much area is covered by which class. Now by crossing them, what we have done, we have generated a CN2 map. Now to correct this CN2 for terrain, we have generated the percentage slope map, and using these two, just a minute. So yeah, so using these two maps and using we have here used the this Horn's formula, which takes into account slope and curve number 2. We have corrected the curve number 2 using both the formulas, Shapley-Williams and Horn's formula. So you can see here curve number 2 is corrected. Now using curve number 2 for each sub watershed we have extracted, and for every day so this is a representation of table, what's the actual curve number, what's the actual area of each sub watershed, and how the improvement due to slope adjustment has happened in the curve number 2 in all the sub watersheds. Now using these two formulas, we have converted curve number 2 to curve number 1 or curve number 2 to curve number 3 based on the antecedent moisture condition. So these are the maps of curve number 2, curve number 3, and curve number 1. Then these are the rainfall, these are the daily rainfall maps, annual and seasonal rainfall maps, and this is the annual seasonal runoff map. So this was the seasonal map, this was the annual map. Now you can see here, this is how the results may look like. Out of 808.25 mm of total rainfall using traditional approach, we are getting 80.97 as a surface runoff, which is so runoff coefficient is somewhere around 10%. Using Shapley-Williams method, it is 78.7, which is 9.7%, and using Horn's method, it is 80.88. So almost similar on annual scale. However, this is for a watershed scale, but when we talk about sub-watershed scale, we could get good improvement. As you can see here on annual scale, the runoff coefficient was in the range of 1 to 23% or 24%, whereas after slope adjustment, the runoff coefficient for each sub-watershed has now ranged between 1.35 to 15.57%. So this appears to be more realistic. Of course, you need to have observed data to validate this. But the point here is, using geospatial data, you can calculate surface runoff. If your model has a routing algorithm also, you can even calculate the discharge from a catchment. So I'll not dwell on these runoffs. Using this curve number method, a tool was developed which is called Soil and Water Assessment Tool, very famously known as a SWAT. So SWOT is a tool. It is a combination of multiple models. It uses SCS curve number method. It uses Mosley modified soil loss erosion, modified soil erosion equation. For it uses it for soil erosion estimation. It uses SWOT for it uses SCSCN for runoff estimation. It uses something else for agricultural pollution estimation. So there are various models. They are integrated together. So this SWOT was developed by United States Department of Agriculture. It's a conceptual plus physical based model because many of the physical processes of let's say sediment movement, crop growth, nutrient cycling, these processes are represented in this model by using directly observed data. And it requires information about weather, soil property, topography, vegetation, land management practices for modeling the hydrological behavior of the watershed. And it's a continuous based model. So it will do it continuously. For every day, the model will run. It's not an event based model, it's a continuous based model. Now, one of my colleague will give you demonstration of the SWOT model specifically for runoff generation because in SWOT model, the curve number method is implemented for estimating runoff. Only difference is it doesn't divide area into sub-watersheds. It divides area into hydrological response units. So it depends on what criteria are defining. The area which qualifies for that criteria will be classified as a 1 HRU. The next area which qualifies for that criteria will be classified as a second HRU. So this is how the area will be divided into different HRUs, and then the model will solve the water balance and soil erosion for each HRU. Now, next such kind of model is HMS. So this is a hydrological engineering service hydrological model system method. So which takes into account the terrain parameters using DEM, remote sensing derived. It also requires land use land cover. It requires soil map. It also requires meteorological data. Now that meteorological data could be remote sensing derived or geospatial data, that could be point scale data. Now after using DEM, HMS calculates the watershed and its morphological characteristics. Then it assimilates land use, terrain properties, soil, and meteorological inputs to calculate surface runoff. However, this is the event-based model. So how it works? It first calculates the total losses. It reduces those losses from the rainfall and then generates the outcome, which is the runoff hydrograph. Then it also has a let's say routing mechanism. So hydrograph of one watershed, another watershed will be routed to the point where you are interested in, and if you have a gauge data, you can calibrate this model to make it as robust as possible to represent the actual condition. So as I told you, it calculates the losses. To calculate the losses, it uses different algorithms, and it requires different inputs. For example, the method that calculates initial and constant loss requires the initial rainfall loss estimation, constant loss information, impervious area information, which can be derived using remote sensing. Now the Heck exponential method requires a value of starting loss, initial accumulated rainfall loss, rate of change of loss, and exponential loss. All these are the parameters that the user has to define. Whereas the impervious area, both the let's say algorithms require, you can give that impervious area using remote sensing data. Now the curve number method requires land use land cover, hydrological soil group, and curve number table. So two of these two can be of geospatial let's say input. Now there's a Halton's method which requires equilibrium infiltration rate, which is a soil property, infiltration rate, which is a soil property, growth index, available soil moisture, exponential soil moisture storage, and impervious area. So most of these are soil properties. Greenarm also requires many of the soil properties to calculate the losses, and then it employs either unit hydrograph or Clark's unit hydrograph, Sanders unit hydrograph, SCS unit hydrograph, kinematic wave theory model to generate a hydrograph. So by deducting the losses, the model will generate a hydrograph. It will route the hydrograph to give you the total runoff hydrograph of that area or direct runoff hydrograph of that area. Now the next model I'm interested in now, because we have very less time, it's already 3:30. I will try to wind up as fast as possible because you are also interested in demonstration. So the next model that we are talking is a variable infiltration capacity model. Compared to all the previous models, this model has a distinct advantage in terms of spatial discretization. It divides area into regular shaped grids, pixels which we call, or cells which we call. Not only division in terms of X and Y, it divides your soil column also into different layers. Layer 1, layer 2, layer 3. It gives you ability to, within one pixel, if you have different vegetation types, it gives you ability to represent their behavior differently for each pixel. So it not only discretize area into small pixels, it gives you ability to further discretize within a pixel for representation of vegetative class or vertically representing the soil layer. As we discussed, this is the advantage, the subgrid variability of vegetation, the subgrid variability of soil moisture storage, the drainage from the lower soil zone, behavior of drainage, which is generally non-linear, is modeled as a non-linear in this model. So there are various advantages of this model. So this is a semi-distributed macro scale hydrological or land surface model. So these are the advantages which already have discussed. That see, this is a vegetative layer. You can divide this into different. So within a one pixel, you can slice it. That half of this pixel is covered by forest, 10% of this pixel is covered by bare soil, 20% of this pixel is covered by agriculture, and maybe the remaining 20% is covered by water body. So this particular diagram here shows that the vegetative layer can further, within a pixel, can further be discretized, further be divided. Within a pixel, you have to define one soil type, dominant soil type, but its variation in terms of depth can be represented. So you can represent the entire soil column into different layers, layer 0, layer 1, layer 2, and you can define their infiltration properties separately. What the model assumes is, at any given point of time, amount of runoff will be equal to the difference between total infiltration capacity of the soil or total water holding capacity of the soil minus the soil moisture in the previous step, at the output of previous step. So if the soil has a capacity to store 10 units of water, and today morning there was 5 units of water stored in the soil, and if 10 units of rainfall happen, then what will happen? Out of those 10, 5 will go as an infiltration in the soil, and remaining 5 will flow as a runoff. And the good part here is, it doesn't assume the linearity in this process, because this behavior of soil doesn't behave, and this will not have a linear behavior. It will be non-linear, many times exponential, or let's say in a generic term, it's a non-linear behavior. So WIC assumes this behavior to be non-linear. That's the advantage of this model. Because of paucity of time, we'll not go into details of this model. I have some of the equations, but we'll only try to use equations which are very essential. So basically, it tries to solve in a water balance mode. It tries to solve the water balance, which says change in storage in water with respect to time is equal to precipitation minus evaporation minus runoff. So this is the basic principle here. And then it tries to calculate all the things. Precipitation goes as a meteorological input. It will calculate evapotranspiration using various physical algorithms and observed data. It will try to calculate surface runoff using property of soil, property of vegetation, property of terrain. So then we will deduct the component of evaporation and component of from precipitation. We will deduct the component of evaporation and delta storage, so we can get the runoff. Or if you know the runoff and evaporation, you will deduct it and you can calculate the change in soil moisture storage. So how it solves it? It will first calculate soil change in soil moisture storage, it will calculate evaporation, evapotranspiration, and it will deduct these two values from the precipitation, and the residual will be your runoff. As I'm sure, so it calculates evaporation from bare soil, it calculates evaporation from water body, it calculates evaporation even from vegetative evaporation. I'm saying the intercepted water will evaporate it. So canopy evaporation it will calculate, as well as it will calculate transpiration also. And it employs the most advanced physical based methods for calculation of evapotranspiration. So vegetative transpiration, canopy evaporation, bare soil evaporation, and it will add it all to calculate E. The surface runoff is nothing but summation of direct runoff as well as base flow. So direct runoff is the runoff that flows on the surface. Base flow is the excess water that the model will have in the bottommost soil layer. So that excess water will be flown out as a base flow, which is a function of, again, the property of that soil and what kind of terrain, what kind of slope you have. So to solve this model, one must provide information about soil, information about vegetation, information about meteorology. And most of these informations you can derive using remote sensing or using geospatial data. So we will see how this model can be implemented using some case studies. So here we have implemented the hydrological WIG model to understand impact of land use land cover change on hydrology. The objectives were to understand the impact of climate change on land use land cover change on a hydrology of a basin. Here the study basin was Pennar Basin in the southern India. So this is a study area, Pennar Basin. Property of that basin is given here. This is a water scarce basin, so estimating a hydrological component is very essential here. Now, what inputs we have used and what inputs were of geospatial nature. So we have used DEM to represent terrain, which is a geospatial input. We have used land use land cover derived from remote sensing data to represent vegetative distribution, which is a geospatial input. We have used soil from NBSS, but we have converted those hard copy maps into soft copy geospatial maps. Again, it's a partially geospatial input. We have used daily rainfall data, IMD's daily rainfall data, but this data is in gridded format. So again, this qualifies for a geospatial inputs. Again, the gridded temperature data also used. Now, what were the steps? The inputs were prepared, the vegetative input, climatic input, soil inputs, and then it was ingested in the model. The model was run, it was calibrated, validated. These all are the variables that the model require. Because we don't have time, so we'll not dwell on these variables and input files. Just keep into mind that you have to give vegetative inputs, static and dynamic, meteorological inputs, dynamic, and soil inputs, which are static. Static means once you give it for entire study run, it will remain same. Whereas meteorological inputs will change from day to day. Even the vegetative library will accommodate the dynamic, like the biophysical properties of vegetation will change from season to season. It will not remain same for all the seasons. So those seasonal or monthly changes can be represented in vegetative library file, which we have derived using remote sensing data. And so these are the different like LAI, albedo, all these things, radiation, all these things are given in vegetative library file. The model was run, and this is how, if let's say runoff under different land use were calculated. Decadal change 1985, 95, 2005 was estimated, and you can see here with this change the peak is increasing because urbanization is increasing and peak flow is increasing. Whereas on the volumetric scale, when we talk about volumetric scale, there is not that bigger difference. Let's say in 85 the annual runoff was 55.75, in 95 it became 53.83. However, In 2005, it has become something around 76.35. It has increased. So what increases? Runoff has increased by 37%, base flow has increased, evaporation has increased or changed. It's not increase, decrease. Now same model can be used for other studies also, like here, because on a basin scale there was no change appearing on surface runoff. What we did the assessment of surface water potential of or the impact of climate change or impact of variation in meteorological properties on entire India or all the basins. So this is how it will look like 95, 2000 and 2005, and the water potential assessment done through this study matches almost equal with the CWC's assessment. Now, as I said, because at the basin scale, no change was appearing, even if there is a land use change, what we did, we went for pixel-based analysis. Instead of comparing runoff of entire basin, we compared runoff of a specific pixel where we know the change has happened. So we have set up a model, calibrated a model, and then we have selected specific pixels where we know a dominant change has happened. Either maybe the forest is cut down and it is converted into agriculture, or the agriculture is converted into urban, or somewhere the water body is being encroached and converted into some other type, or somewhere the new water body has been established. So such areas where dominant change has happened, we have selected them, and then we have compared. What we understood here is, on a basin scale, why we are not getting any quantitative difference? Because within a basin, somewhere a change is happening which is increasing runoff. Somewhere else, change is happening which is decreasing runoff. And these pixels somehow cancel each other's effect. Unless and until you have change in a basin in only one direction, that the vegetation is losing and urbanization is increasing everywhere, then only you will have some numerical impact on a basin scale results. Otherwise, the impacts will be local, which we have proven using this method. Now, this kind of models can also be used to understand impact of climate change. Now, this WIC model we have implemented on Krishna Basin. Again, the inputs used were DEM, land use land cover data, then meteorological data. So the model was set up, the model was parameterized, calibrated. Once that exercise, so this is the let's say calibration chart, this is a validation chart. Once we got to know that model is performing well, what we did then, the model was exposed to the future climatic scenarios, RCP 4.5 and RCP 8.5, and then we compared or we analyzed the behavior of climatic parameters and the surface runoff. So what you can see here is annual precipitation in both RCPs 4.5 and 8.5, though it shows increasing trend, but not at that order. However, the temperature is showing dominantly increasing trend in both the RCP 4.5 and RCP 8.5. Now, when we implemented this on those RCP 4.5 or 8.5, when we have ingested that into hydrological model, what we could, obviously because rainfall is showing positive trend, the runoff is bound to show positive trend. So in RCP 4.5 and 8.5, what we have understood is there will be a increase in total runoff. Along with that, what is going to increase? The peak flow is going to increase. As you can see, the maximum discharge from 85 to 2004 was something around 34,000 cubic. Whereas if the climate change scenario is to be true, the discharge will exceed even 1 lakh cubic. This I'm talking about peak flow. I'm not talking about total discharge. I'm talking about peak flow. So one, number of flood events and the quantum of flood or the severity of flood, it will increase with the increase in or with the effect of climate change. Now in this case, all of you must understand this model was implemented considering the basin as a virgin flow condition, which never happens in India. So though the peak flow is increasing, if you have good storage capacity, like most of the southern Indian and central Indian basins have, like Krishna and Godavari basin have a storage capacity of around 40% of their annual water potential. So in those cases, if water management plans are robust, they are well drawn plans, even with the climate change, we might not have to worry about flood, but we may have to worry about the lean season flow. That's a different aspect. Now, in the concluding part of my presentation, I would like to tell you, since last one and a half hour, I was talking about what inputs you can use in hydrological modeling. So I would like to tell you what are the
उनकी तरफ से नहीं आ रहा, हमारी तरफ से तो चल रहा। वही देख रहा था इधर से तो।
Sir, am I audible? Sir, am I audible?
Get this data. So what I was saying, the primary site for all the observed data related to water resources is India IIRS, India Water Resource Information System. On this site, you can get observed data of groundwater, observed data of surface water, observed data of reservoirs, even glacial lakes, many reports. So all this data is available on this website, and this website is hosted by Central Water Commission, Ministry of Jal Shakti. ISRO also has few sites on which it disseminates data. So one of such site is Bhuvan. So this is ISRO's own geoportal. So you can have Bhuvan 2D or Bhuvan 3D. On this website, you can get satellite data free of cost. Even you can get thematic maps like land use land cover map, even the geological maps, Cartosat DEM will be available, and many archive maps which are available on ISRO's server. You can access it. Many of them are available for download. Few of them which are not available for download are available as WMS, web-based service. So you can call it in your GIS software, you can use it wherever you require, and you can switch it off when you don't require it. One such website where you can get meteorological data is IMD AWS website, where all the IMD AWS are the data of IMD AWS for last, I think, 1 week will be available. If it is a rainfall data or other meteorological parameters, they will be available, but the limit is it is a dynamic data, and last 8 days data you can get from this website. If you require long-term data, then you have to purchase it from IMD. IMD also provides you gridded meteorological data. So for entire country, so precipitation data is at quarter degree by quarter degree resolution. Then temperature data is at 1 degree by 1 degree resolution. So you can download it. You can do little bit of pre-processing. Nowadays, it is also available in NetCDF. Many of the advanced models require input data in NetCDF only. So it is available in binary format also. It is available in NetCDF also. There is one more website of ISRO which is called MOSDAQ. On MOSDAQ also you can get satellite derived product, you can get in situ products. Like on MOSDAQ, ISRO also has some AWS, so that AWS data will be available. Some of the AWS are with collaboration with IMD. Those data will also be available on this site. Satellite altimetry data. Now those of you who are aware about altimetry, we can use altimeter for water level monitoring. So satellite altimetry data for many of the locations in India is available on this website. There is one more website called Vedas, visualization of earth observation data and archival system. On Vedas, first of all, huge amount of data is available. It is uploaded dynamically, it is updated. Along with that, you can build your own processing. Well, you can't build high-end processing tool on this, but all the preliminary processing tools can be built on this data. So you can take maps and you can run your query, you can highlight area, all those things. Those tools are available, and this is hosted by Space Application Center, Center of ISRO. And these people are very cooperative. If you have something in your mind, you want to customize your own application, they will help you. They'll extend fullest help possible. Now the satellite based altimetry based water level data for many of the rivers, as I told you, is also available on Vedas. Even the water discharge using basin water index results are also available on these websites. Similarly, there are number of such sites which, like soil map, global soil map is available on FAO website. Many of the remote sensing data like Sentinel data is available on Copernicus. Sentinel 1, Sentinel 2, Sentinel 3 data is available on Copernicus website. Landsat, NASA's remote sensing data is available on Earth Explorer. Many of these data sets are also available on Google Earth Engine. And the best part is Google Earth Engine also has a humongous power of analyzing that data. You just need to know how to code that. So all that data is sitting on Google's, let's say, storage repositories. You just have to call that data, write some code that, okay, I want to calculate NDVI, and then I want to take a temporal profile of it. Write a code, fire the command. It will not consume any of your memory. You just need a decent internet connection and a account in Google Earth Engine. You can fetch that data, analyze that data. You can store those results on your Google Drive, and whenever required, you can download those results and reproduce those results. These are only few. Like there are many, let's say, websites or portals where you can get data free of cost, as well as you can get softwares to download. If you don't want to download, the websites will have their own servers on which your request will be processed and the results will be sent to you. So what I was trying to say here is hydrological modeling is a very vast domain, but you can start working on it. Data will not be a problem. All the data that you require, excluding some of the confidential data, like many of the transboundary river data may not be available in public domain. For that, you have to contact appropriate authorities. But all remaining data sets, or all other remaining research, let's say, basins, the data is available on portals free of cost. So you just need to know where it is, how to use it. So I tried to explain one or two models in this lecture,